Tiago Fernandes talking to us. So Tiago has done his master here under the supervision of Vitor Cardoso, and currently he's doing his PhD, supervised by Professor José Lemos, and supervised by Vitor as well. And I'm also, well, I'm very happy that he stepped up to talk, because I was having some trouble with the speaker schedule for this week. And I understand he also has very nice results he would like to tell us about. So without further ado, please, Tiago.
Thank you. So I'm going to talk about black holes in the grand canonical ensemble, as the title suggests. So, because this is a seminar and it's going to be quite long, I'll present you an overview of the presentation. So first I'll go through the initial motivation and I'll make a summary of some previous works, first by Gibbons and Hawking, André, Lemos. Of course, I'll first talk about the formalism that they use, and in the end I'll use to build the canonical ensemble and the grand canonical ensemble for black holes. This is just the first part. In the second part, I'll talk about my current work. I'll make a summary what I've been doing with Lemos. It's still not published, but it shall be this year. And then I'll finalize with the summary and the future work. So before I start talking about thermodynamics and the black holes, I need to talk about how this kind of started. So there was this paper by Bekenstein and Hawking where they described the 4 laws of classical black hole mechanics. This here is the first law, and it describes, it's a formula that relates two black holes that are stationary, and they are very close in the parameters that describe the spacetime. And what this tells us is that the difference of the ADM mass in these two black hole configurations is given by this formula. So this is kind of a difference of the mass formula for black holes. And as you can see, this ADM mass will depend on variation of the area of the event horizon. And in this case, for rotating black holes, it will depend on the difference of angular momentum of black holes. And well, this is a classic law, okay? This doesn't have a priori anything to do with thermodynamics. But Ken Bekenstein in '73 thought about this, and he thought about adding what would happen if one adds quantum effects. And he thought that, well, if there are quantum effects, maybe the black hole should be thermodynamic. And actually, this first law should be a classical analog of the first law of thermodynamics of the black hole. So this ADM mass would be the internal energy of the spacetime, and from the first law of thermodynamics, there is a term which is PdA, which is the pressure times the difference of the area, but the pressure of a black hole is 0 because there is no matter. This term here of the angular momentum will be an analog for the chemical potential times a difference of the particle number. And there's only a term remaining, which is temperature times the difference of the entropy. And what Bekenstein hypothesized was that this TdS would be equal to this term here. So the entropy of the black hole would have to be a function, or in the end, it says that it should be linear on the area of the event horizon. Then there is a constant here remaining, where he estimated by heuristic arguments what would be the value of this constant. But this was then later determined by Hawking in '75. So he considered a spacetime where matter was collapsing into a black hole. And then he analyzed through QFT inverse spacetime what would happen to a quantized field. And if we start here with a vacuum state of a scalar field, for example, then he found out that an observer at future null infinity would observe that the quantum field would have a thermal spectra. So with this temperature, which is proportional to the surface gravity of the black hole. So it would seem to this observer that the black hole was emitting a radiation at this temperature. And if you do kind of a leap of faith, like you do in thermodynamics, if we consider that the black hole is a black body and it's in thermal equilibrium with this Hawking radiation, then in the end, the temperature of the black hole will be equal to the temperature of the radiation, which is the Hawking temperature. And if we know the temperature, then we know by certain that the entropy will be given by this, where you have the coefficient 1/4. This area here is just the Planck mass, it's just the gravitational constant. And so this is the so-called Bekenstein-Hawking entropy of a black hole. But, well, classical black holes have entropy equal to 0. So there was not actually something fundamental that explained this entropy. So this begs the question of what is the origin of this entropy? And is there something more fundamental to this that explains this entropy? Moreover, we can investigate what is the link between statistical mechanics, which gives rise to this entropy, and gravity itself. This can only be done if we have some new fundamental theory. It can be some new exotic fields that are coupled to gravity, but I think that one of the most famous is the one of thinking that there is some kind of quantum theory of gravity that explains the emergence of this entropy of the black hole. And this is the path that I'm taking. So I'm taking the path of making the quantization of gravity through the path integral approach, and then make a kind of semi-classical approximation to compute the thermodynamics. But first, I'll give you a summary of how to do this. First, in quantum field theory, you can quantize your theory by the canonical quantization, which is you put your fields and you turn it into operators. But there's also another method of quantizing your theory, and this is by the functional method. So you can have these functionals, Z of J, which are path integrals of the field that you wish to quantize. And this is the Lagrangian of the field. And this is J phi. This is just for variational purposes. And with this functional here, you can make variations of this J. What will happen is that the phi here goes here, as you have this path integral. And this will actually be a way of getting the endpoint correlation functions of the theory. Here is the 2-point correlation function, which is actually equal to the Green's function of the theory. So with this, you have a complete description of the quantum field theory. So this is the main thing. Hawking, in his book, General Relativity, he has a chapter on how to quantize gravity through this approach. And actually, the start is simple, which is, well, you do the same thing. So instead of having a field phi, you put the metric and you put the Einstein-Hilbert action, you need to add a boundary term here. This is the Gibbons-Hawking York boundary term, which it shall appear later on. And of course, you need to impose some boundary conditions to this path integral. So there are actually two ways of dealing with this path integral. But one is stay as it is. But here I'm going to take the Euclidean way, which is, so first we analytically extend the action to the complex numbers, and we perform a Wick rotation. So in the path integral, this would mean that we have an Euclidean metric, an Euclidean action. The good thing of this is that this kind of path integrals with these integrants are they are well studied mathematically, but still it has some problems. So the first thing is that if we consider the Einstein-Hilbert action with the boundary term, Hawking showed, and Hawking and Gibbons showed, that this action here is not bounded from below, so it can be negative indeterminately, and so the path integral should diverge. There's also a problem of defining what is the measure here to perform the path integral. Here it's not, it is very difficult to define it in opposite to quantum field theory, which comes out from the canonical quantization. There's also difficulty on the passage from the Lorentzian to the Euclidean side, which is we lose notion of causality because this is Euclidean, so we don't have a notion of an exact notion of time. Still, it seems that this thing is well behaved when we make a zero loop approximation, which is just taking the contribution of these integrants in the classical path or perturbations near this classical path. And with this, we can make like a semi-classical approximation of the path integral, and we can use this to build statistical ensembles.
Sorry, a very nice question. Is this Wick rotation required for the construction?
No, well, it is a way of doing it. Okay. There is also other ways that deal only with the Lorentzian way, but that is also has associated a lot of problems. Okay. But well, what can one do? But here I'm going to use the Euclidean path integral. Yeah. Yeah. Do you know what would happen? Can you do something like that here? Yes, you can. You can impose like constraint equations, but still, there is not. This is not well formulated. But yes, you can impose some constraint equations, like adding some terms here that fix the kind of the gauge as well. Here, what I'm going to work on are static or stationary spacetimes, so don't have the problem of gauge fixing. Okay, so we can calculate the path integral with this zero loop approximation. Okay. Now, how can we relate this? How can we use this to construct grand canonical or canonical ensemble? Well, from statistical mechanics, we have that a partition function of a system describes the thermodynamics of the system if we make derivatives of Z. We can obtain the grand potentials, the energy potentials, and so on. And this partition function, this is for the case of grand canonical, it should be given by this. This is just the sum over all possible states with this contribution here. H is the energy or the Hamiltonian. But we keep beta, which is the inverse temperature, and phi, which is some chemical potential, and that is a constant. Okay, these are some value. But it turns out that from quantum mechanics, if we do this for quantum mechanics, we can actually derive that this thing is actually in the path interval, which is something like this. For gravity, this path from here to here, it's not clear, but we assume that it is a given. So in the grand canonical ensemble of a spacetime, one would have this path interval, where this is the Euclidean action. This is the Euclidean metric that we are going to integrate over. These are some matter fields that are here because it's the grand canonical. And this partition function will depend on data on the boundary of the spacetime. Here, beta, which is the inverse temperature, is going to be the time length at the boundary of the spacetime. Phi will be some value of the matter field at the boundary. And this P here, it's just additional data on the boundary that one must impose. There's one important boundary condition, one important condition for this path interval is that this Euclidean metric must be periodic in the time coordinates. This comes exactly from the passage from here to here. So we can put, there's a way of doing this. I'll not explain much. And by the way, doing the canonical is just erasing phi and the A. So it would become the same, almost the same. So from the path integral that we have before, we can only consider the classical path. And by doing that is basically imposing the Einstein equations to the metric and the matter field equations to the fields. And in the end, one would have a partition function given by this, where this is just the action of the classical path. Of course, these equations need to be defined by the boundary conditions that one has, which is beta, phi, and the additional data boundary. Then there is an easy way to relate this to thermodynamics, which is in the case of grand canonical, the partition function is directly related with the grand potential of thermodynamics, and the canonical is directly related to the Helmholtz free energy. So we can make the identification of the action being equal to beta W or beta F in the case of canonical, and then through the derivatives of this free energy, one obtains the thermodynamic quantities of spacetime. Now, of course, for this to be valid, these classical paths need to be a minimum of the original action in the path interval. If it's not the minimum, then this is not this is not valid. So our calculations are not valid. May be only valid at a certain point on time, but in all time it is not. Okay. And we also can then compare with other thermodynamic configurations and see which one is more favorable. This can be important on seeing if there are some kind of phase transitions from one configuration to the other. Well, no, the boundary here, is a time-like hypersurface. So it's an history of like, for example, in my case, it's going to be a shell at radius r, and the time-like hypersurface is going to be the history of this shell. So this establishes a boundary of the spacetime. Here, we do not consider space-like hypersurfaces because they are connected with each other, because it's periodic. So there's only time-like hypersurfaces. Okay, now this is the formalism. First guys to apply this approach were Gibbons and Hawking. They applied this to very large spacetimes for Kerr, for Schwarzschild, and for Reissner-Nordström. And they obtained this kind of action, and they obtained the Hawking temperature, the electric potential, and they obtained Bekenstein-Hawking entropy. So they recovered all the results that have been obtained from saying that black hole is a black body that is in equilibrium with Hawking radiation. The thing is, in these calculations, they obtain a negative heat capacity. And this means that these configurations are not stable and they do not minimize the action. So these are actually not, these calculations are not, zero loop approximation is not valid here. Actually, Gross, Perry, and Yaf obtained that, for example, the Schwarzschild configuration was actually a saddle point of the action. So we have, they have this kind of issue. But then he came York and he proposed to analyze the Schwarzschild black hole, but with a finite cavity. For example, if we impose a spherical cavity with finite radius, and we found that there are actually two solutions. One where the black hole, which is the smallest mass possible for the black hole, it actually corresponds to the Bekenstein-Hawking solution if we put the radius of the cavity very large to infinity. But then there's actually another solution which has a larger mass, which is actually stable. So with this one, we can make thermodynamics. There were also other works by, for example, Martinez and York, where they analyzed the additivity of the entropy for example, a black hole, and then consider a shell of matter here. The work of Radon and Hall, where they generalized this for a charged black hole, but on equal dimensions. Then Pesse and Lemos, they did this for Reissner-Nordström ABS, and there are many other works. I'll end up this part with talking about with the generalization of the Schwarzschild black hole in a cavity for 5 and higher dimensions. So for 5 and higher dimensions, the equation that determines the solutions for the black hole in equilibrium with the cavity is this equation. The solutions are here described. I think this has to be for a given dimension. So as you can see, we still have 2 solutions, and the one with the larger radius or the larger mass is the stable one. And there's actually a very nice condition which states that the stability, what conditions the stability of one of these solutions is that the R plus needs to obey this condition, which is basically saying that the R plus over R needs to be needs to be smaller than the photon field. Needs to be superior to the photon field. So for the higher R plus, well, we can also do this for R plus, for the smaller R plus, but well, it has the problems that it has. So from the action evaluated in the classical path, we obtain the free energy, which is given by this. This already assumes a shape of beta times energy minus entropy. We can, from this, derive the other thermodynamic quantities through derivatives of the action in beta, yes, and R, big R, which is the radius of the cavity. And the energy is given by this, which is the quasi-local energy evaluated at the cavity R. This is the pressure, which is analog to the pressure of a self-gravitating thin shell. And this is the Bekenstein-Hawking entropy for the dimensions. So, yeah, everything is fine. But there is also the realization that for R plus 2, the capacity is positive, so it's stable. But for R plus 1, it's negative, so it's unstable. And this should be taken with a grain of salt for the case of R plus 1.
What are these expressions which are not in D by the greater? It looks like you just evaluate them in D plus 4.
Sorry?
You said that these were for D that were final rating.
Yes.
So what goes wrong if I just take D equals 4?
No, you can. Yes. This is just a generalization for higher dimensions. Maybe I should have been more careful with the language of the title. But it is also valid for the equals 4.
But the equals 4 is what you're.
Sorry?
The equals 4 is what you're.
Exactly, yes. And André and Lemos did this first for 5 in a paper, and then in the other paper we did it for D.
The higher dimensions, are they inspired from higher dimensional theories? Or?
Yes, exactly. So the main motivation of doing this is that first there are theories that require higher dimensions, but actually there is also another application of this for black brains. So the stability of black brains, the dynamical stability, there is a conjecture that says that dynamical stability is equal to thermodynamic stability. So this can be used also in that. Okay, so we have the thermodynamic quantities. And in principle, we should have the problem resolved. But then we also wish to compare this configuration with for example, the hot flat space, and see if which one is more favorable. So we could have a flat space-time, but if the black hole is more favorable, then it could have a phase transition between these two. The better way of analyzing that is by building a generalized free energy. So we basically go to this expression, and instead of considering R plus 1 or R plus 2, we consider R plus to be free. Of course, then the classical path will be given by extremizing F bar. In the literature, this F bar is related to the reduced action, which is by imposing the constraint equations into the initial Euclidean action, one would obtain a path integral like this. So we restricting the paths to follow the constraint equations of the field. Now, this is a nice plot in André and Lemos. This is the generalized free energy. And the main point is to compare this point here, which is flat space, is basically flat space without anything. And then this point here, which is the sort of the solution with higher radius. And the passage from here to here, you have kind of a barrier potential. But this is more favorable if it is negative. This is always zero. And they found here that this will always be favorable if the R plus of the black hole, R plus over R, is higher than the Buchdahl radius. And so you have Buchdahl radius, you have photon sphere radius. There should be some kind of connection to matter dynamics, but it's still not, apparent the reason why. Instead of comparing with hot flat space, they also compared with quantum hot flat space. Basically, just consider a space of hot gravitons. So it's like hot photons, but with spin 2. And this is the free energy. And so here is a plot where here the black region is where the black hole is more favorable. In the gray region is where quantum hot flat space is favorable to the black hole configuration. And in white is where there is no black hole configuration, so it will always be quantum hot flat space. And yeah, with this, I conclude the first part. Are there any questions?
Yeah. I have one. In the previous slide, sorry if it's a silly question. How would the qualitatively the upper plot change if it was like d equals 4, for instance?
Well, d equal to 4 will kind of bring this point here more closer to 0.
Okay.
But the general behavior is going to be like dilation or contraction of this graphic.
Okay.
But the general qualitative behavior is always the same. This is actually a nice property of all of these is that it seems that for higher dimensions the qualitative the qualitative behavior is the same. Okay. I shall go forward to the second part. Then, so my part now is to do the same as André, but with a charge. So we have a cavity in d dimensions with radius r, and we consider the partition function of the spacetime as given by this. This should be Euclidean metric. This A is the Maxwell field, and the Euclidean action is given by this, where this is the Ricci, this is the dynamical Maxwell term, and this is the so-called boundary term, which is the Gibbons and Hawking York boundary term. And now something that is pretty cheeky, which is that we only consider configurations for the spacetime that follow this metric. So we impose spherical symmetry, which is actually, it's not really true, but this is an approximation. So from spherical symmetry, we have that the Maxwell field only has one component, which is A of tau. Also, I forgot to mention that tau runs from 0 to 2 pi. because it's periodic, and we consider radius is not actually, it's a radial coordinate from 0 to 1, but notice that this r, which is actually the radius, it is something that is being integrated on the bottom plane. So now we need to impose boundary conditions at y equal to 0 and y equal to 1. Y equal to 0 will be the same thing as saying that it's going to be the radius of the event horizon. Y equal to 1 is going to be the radius at the cavity. Y equal to 0, we would say we impose this condition here, which basically tells us that there are no conical singularities of the spacetime. This condition here and tells us that, and this one here tells us that the y equal to 0, if we go back to the Lorentzian method, we would have a killing horizon. For d equal to 4, this argument here is easier because you just say we want to impose an Euler characteristic equal to 2, but for higher dimensions, especially for odd dimensions, the Euler characteristic, there are some difficulties to define it. So we just say that it is a killing horizon. We also put the boundary condition to a tau being 0 at the horizon. Now, the boundary conditions at y equal to 1 are given by these two conditions. So we would say that beta is going to be 2 pi b evaluated at 1, and this is constant. And so beta is going to be the time length, which is going to be inverse temperature. And this defines the value of the electric potential at the radius, or at the cavity. Now, we have this path integral to solve with the boundary conditions. What I'm going to do is first obtain the reduced action, and then extremize the reduced action and obtain then the black hole thermodynamics. And so first I need to impose the Gauss constraint, which tells us that it basically turns the a tau into a charge that it can depend on tau, on time, because we are not imposing evolution equations. We impose also the Hamiltonian constraint, which restricts r prime over alpha to be given by this, which is the typical f in Reissner-Nordström. But notice that r plus here is a functional. It may depend on tau and q as well. So in the end, also this means that one can make coordinate transformation. So we can pass from y to r, and every change of coordinates that we imagine will always give rise to the same configuration. So we take out the r. Imposing these two conditions, we have the reduced action given by this. R plus and q are functionals. This integral on d tau is just a formality. And as you can see, as in the case of André, this assumes like an expression of beta times energy minus q beta phi minus entropy. So we make the variation on these functionals r plus and q, and what we obtain are the typical expressions for the inverse temperature and the chemical potential. In this case, it's the electric potential. And so this, since beta and phi are constant, this sets r plus and q. Now we will need to invert this to find r plus and q. We are going to obtain a polynomial equation for r plus. Just like André's case, it's not solvable analytically for d dimensions, for a general d, but one can pick a D in which one has, for example, a quadratic equation, and that is the case of D equal to 5. So in D equal to 5, one would have an R plus given by phi and beta. Here I write right away the temperature. And well, the Q, you just multiply R plus with R minus, and you obtain Q squared. And so this is the shape of I star. And these two points here are the two solutions by exchanging here the sign. Turns out that this thing here is going to be a saddle point of I star, so it's not going to be stable. But this point here, which is the larger R plus over R, is going to be stable. It's going to be a minimum. This here plotted is a plot of R plus over R. And as you can see, there is a range here where there is no solutions, and this will depend on the quantity phi. But then if you fix phi, you'll have a solution here, and then this will split in two, just like in André's case. But the thing is here, what happens differently from the André's case is that the larger radius here is going to reach the radius of the cavity in a finite temperature, in opposite to André's, where you need temperature equal to infinity for that to happen. And we think that's an effect of having a charge on the system. This is just to explain how to compute stability for these two extrema. So you analyze the Hessian of the reduced action, and then compute this Hessian must be positive definite for the extremal point being a minimum. And actually, the only point that obeys this is the larger R plus. One can prove for D, general D, that R, the smallest, is always unstable. I was not able to prove this for R plus being always stable. I instead ran a program that checked that for every D, and I got that for at least for D equal to 4 until D equal to 100, this will always be a minimum, so it's going to be stable. The thermodynamics then can be given by doing the derivatives of the here in this case, the grand potential. We would obtain that Q is going to be equal to Q, which would be expected. Notice that Q here shall depend on beta and phi. I'm not putting the explicit dependence on beta and phi. The energy will be again the quasi-local energy. The pressure will be again the pressure of a self-gravitating shell with a charge. And the entropy will be again the Bekenstein-Hawking entropy. Now, for the final part, which is the same thing that André did for the uncharged case, is to compare this black hole configuration that is stable with some kind of hot flat space that it is charged. We had a lot of difficulties to understand what is that configuration because of the boundary conditions that we have imposed. So typically the electric potential, if we just consider a point like charge, it would blow up. So it didn't make much sense. So in this case, we thought that maybe the flat space, the hot flat space would be just a conducting sphere with a charge and a fixed radius. So this avoids the blow up of the electric potential. And but the thing is, you have another variable, which is R0, which is the radius of the conducting sphere. Still, here is a graph of the most favorable configurations. Here, the gray is where the black hole configuration is the most favorable. In white is where there's no black hole configuration. So this configuration will always be favorable. And then these lines here, this is for a fixed R0. This is for each value of R0 over R. From these lines downwards, the configuration of a conducting sphere is more favorable. And so with this, I'll conclude. So what I want you to keep in mind is that first, black holes are thermodynamic objects. One can build the grand canonical ensemble and the canonical ensemble of a black hole or a spacetime with even matter through the path integral approach. For a very large cavities, or cavities that are at infinity, the configuration that arises for the black hole is unstable. But for finite cavity, if you put a finite cavity, you will generally have two solutions where the one with larger mass is stable. This qualitative behavior extends to higher dimensions, and one can analyze phase transitions between hot flat space in these black hole configurations. Now in the future, we still want to work out what is the hot flat space in the charge case, and even the quantum hot flat space. It's going to require some time thinking about it. And we want also to make the same thing as Martinez and York, putting, for example, a thin shell of matter and see if the entropies of the black hole and the matter add each other. And yeah, I think that's it. Thank you.
Very well timed. Thank you. Do we have questions? Oh, sorry. Who was first?
Yeah, thank you very much. Can you highlight what the difference when comparing with André to charge? Other than the
Yeah. First, the main difference is the use of the formalism. Instead of having canonical, we have grand canonical. So we need to fix an additional parameter, which in this case is the electric potential. This is a chemical potential in many other systems. The major difference in the configurations that one has that are in equilibrium with the cavity is that the larger solution will heat the cavity if for a finite temperature. Which in the case of Andrés, this would go to an infinite temperature. So this is actually something that we're trying to figure out why. I think Lemos knows the answer.
Okay, thank you.
Can you go to the next slide, please?
Next.
Yeah, the next one. When you
This one.
check for the dimensions, let's say you find that from the 4 and the 100, it's stable. How many did you check?
Yeah, I checked from the equal to 4 to the equal to 100.
Like, you check above 100 happens, or
I did not check, but I mean, it's a conjecture.
Induction.
It's because this condition gives rise to another polynomial. So it is, and you cannot find the zero of that polynomial analytically as well. And it seems that for D, this zero increases. the zero of the polynomial that gives rise to the stable configuration also moves, so you don't know which one moves faster or not in the proof. So I don't know.
Just curiosity, and because I guess that you have to test infinite field.
Yeah. I just tested to d equal to 100. I have like a problem that checks for every d and compares the value.
And do you know why you're in why 0, 1, and 3, 1, and 2, and 3 don't consider stable?
Oh, well, for d smaller than 4, there are definite problems in formalism. So you notice that here, for example,
Yeah.
Yes.
d minus 3, and here also 2d minus
Yeah,
6.
You have 0 also d minus 3 and d 4, 5.
I think they also have black holes.
Yeah. I think it has to do with that.
Yeah. I'm not sure why maybe it has to do something to do with that, but okay. Thank you very much.
Oh,
I have a question. So are you not giving me the motivation for the chemistry, right? Because this some black hole, but is there any physical motivation for the chemistry itself, or is it just because because I understand that without the chemistry, that it was a previous work, right?
Mhm.
Where they were always unstable.
Yes.
But if I mention a black hole in the universe, then I'd be wrong.
Yeah, but yeah, that is a fair question. Well, there are two. Well, I've thought about what this means on our universe. Well, you could think about the black hole that is interacting with something that's not at infinity. But that would mean that that something has infinite energy because it's a heat reservoir. So it's not very physical. I don't know actually the answer to that. But this is the other part of the answer is that considering a shell, a cavity with finite radius is actually analog to consider ADS spacetimes. So, and this has many implications in ADS CFT, all of that.
I'm a little bit confused about the notion of phase transition.
Yeah.
Because you say, so you've got sort of say some set of thermodynamic parameters,
Yes.
and then there are two possible states,
Yes.
and one of them is more favorable. And then you say, well, you know, that means maybe there would be a phase transition.
Yes.
But you've got dynamics. So what actually drives the?
Yes.
What does it mean?
Yes, that is true. But the only way of doing that, well, you can consider all the paths on the path integral, and
But even then, you'd be restricted to the case of stationary or static spacetime, right? So it's not dynamics. Is that right? In your path integral setup, you're enclosed there already, but it's symmetries so it's stationary.
yes, but only if you impose the evolution equations. Because here in this case, I did the zero loop approximation, but one wouldn't know, for example, if we took all the contributions of the paths that are not even physical, what one would obtain. Because in the path integral, formally from initial considerations, we are not imposing evolution equations. So it might not even follow the evolution equations. So I think that the argument is that if you have two configurations that they can be calculated by zero loop approximation, and they have the same parameters, beta and phi, the actual true path integral we'll have this configuration taking into account the other configuration and the other paths. So it may be that the one that maximizes the most of the action is going to be the one that determines the final configuration. So it's in that sense. So, for example, if you in the points where both contribute the same to the path integral, this is like some point of critical. It's kind of a critical point. It's in that sense. It's the phase transition index in that sense. It's not dynamical, as you said.
Are there any other questions? Okay, so given the time, I think we can leave it here then. So thanks, Tiago, very much again.
If you enjoyed the video, like and subscribe.